Good morning everyone. Today we are going to see Operating System Unit 3 Session 12. In the previous session we have studied the Dining Philosopher's problem using monitor. In the Dining Philosopher's problem we have seen there were 5 philosophers and they wanted to eat the noodles but there were only 5 chopsticks. If all the 5 philosophers picked the chopstick at the same time, then none of the philosophers were able to eat and they were stuck there. So none of the philosophers are like processes. So none of the processes are able to perform their task and all will get stuck there. And this situation results in a deadlock. So when all the processes are not able to perform their task, then this situation results in a deadlock. So in today's session we are going to see how this deadlock occurs and how to avoid the deadlocks and how to represent those deadlocks in a graph format. So when an operating system wants to access any resource, it firstly sends a request to a particular resource which it wants to access, and then it utilizes the resource and finally releases the resource after using it. So how is the working of the processes and the resource? So whenever any processes wants to use any resource, first they will the request to use the resource. If that resource is free, then that resource will be allocated to that process. And after using it, then the process releases that resource so that other process can use it. Now for suppose many processes are trying to access one resource at the same time, then it becomes difficult to provide one resource to all the processes at the same time. In such situation, the concept named deadlock arises. So the problem arises when all the processes or many processes are trying to access the same resource at the same time. Then it is not possible to allocate the same resource to all the processes at the same time. Then in such situation, the deadlock arises. The definition of deadlock is, deadlocks are a set of blocked processes, each holding a resource and waiting to acquire a resource held by another process. So the definition of deadlock is nothing but the blocked processes. That is, a process is already using the resource and again it is holding some another resource. Then this situation creates the deadlock. Example, there are two cars, one car is coming from this side, another car is coming from this side. If both the car comes, obviously they are going to clash it. Now this creates a deadlock, both are stuck there and we need to solve these deadlocks. Okay, before the clash arises, before they enter into the deadlock, some of the process has to, that means some of the car has to move backward, one of the other car has to move backward or take the side so that both the car can pass from there. If both the cars stuck there and none of the car gives the side or takes backward, then they are going to enter into the deadlock. So this is how the deadlock is. This is the resource 1, this is the resource 2 and process 1 and process 2. Now resource 1 is assigned to process 1 and resource 2 is assigned to process 2. Now see, already the process 2 is assigned resource 2 here and process 2 is also waiting for resource 1 here. And resource 2 is already assigned, resource 1 is already assigned to process 1 here and process 1 is waiting for resource 2. See, in this case none of the processes are going to release it, all the processes are going to stuck there. Then because they are waiting for each other resources and they are holding also each other resources, this enters into the deadlock. See, there are two resources R1 and two processes P1 and P2, where R1 is assigned to P1 and R2 is assigned to P2. P1 wants to access R2. As we already know, R2 is held by P2. And now P2 wants to access R1, which is P1 executes only when it gets access to R2. Also P2 executes only when it gets access to R1. So this situation is a deadlock situation. If you want the flow proper between the process and resource, then the process has to first request for the resource and then wait until it becomes free. And once they get the resource, they are going to use it and they are going to release it. So after releasing, then only the other process can use it. Then there must be the proper flow between the process and the using of resource does it properly. So there are necessary conditions for resource deadlock. So these conditions are very necessary, and if these conditions meet simultaneously at a time, then the deadlock arises. So deadlock situation can arise if the following 4 conditions hold simultaneously in a system. So there are 4 conditions. If they occur simultaneously in a system, then the deadlock arises. So which are those 4 conditions? First one is mutual exclusion. So allow only one process at a time to execute. That means at a time to use one resource. So allow only one process to use a resource at a time. Hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other process. So hold and wait is it is already using some resource and it is also waiting for other resource. Then this is hold and wait. No preemption. Once the resource has been allocated to the process, it cannot be preempted. It means resource cannot be snatched forcefully from one process and given to other process. The process must release the resource voluntarily by itself. So no preemption means once the CPU is allocated to any process, it has to complete its task. If there is in between the interruption all the time, then that process may not able to complete it. So there must be no preemption, and if the preemption occurs all the time, then the deadlock arises. Circular wait, that means the processes are waiting for each other resources. So a set of processes are said to be in a deadlock if one process is waiting for other process which is allocated to another process, and that process is waiting for a resource in a circular form. So we have already seen the diagram of this. So first we will see this mutual exclusions. There are 2 processes and there is one resource. So at a time allocate one resource to one process. At a time allocate one resource to one process. So don't do in this way. At a time don't allocate the same resource to multiple processes. So this is the wrong way. Then it enters into the deadlock. This situation enters into the deadlock. So when process A finishes using resource 1, then give the chance to some other process. Hold and wait. See already the process A is using, already the resource 1 is allocated to process A, and it is also holding resource R2. It is also holding resource R2. So even this should not happen because R2 can be used by some other processes. So even this situation can create the deadlock. Circular wait is this, which we have already seen. So resource 1 is allocated to process 1, and process 1 is also waiting for resource 2. Resource 2 is already allocated to process 2 and waiting here. So this circular wait, obviously it is going to create the deadlock. So if any one of these processes, processes holds the condition, that is mutual exclusion, hold and wait, no preemption and circular wait, then it enters into the deadlock. If any one of the, that means all the conditions should be hold, all the conditions must be performed simultaneously, then the system enters into the deadlock. Resource allocation graph. So we can represent the deadlock in a form of graph. That is, a resource allocation graph is a pictorial representation of the state of the system. So we can understand in which situation the state of the system is, which process is using which resource. The resource allocation graph is the complete information about all the processes which are holding some resources or waiting for the some resources. So when you observe the resource allocation graph, complete information will get which process is holding which resource and which resource is used by which processes. It contains all the information about all the instances of the resources, whether they are available or being used by the processes. So if there are 4 printers available, then you will understand which printers are occupied and which printers are free. So in a resource allocation graph, the process is represented by a circle and the resource is represented by a rectangle. So processes we represent in a process 1, process 2 and so on, and resources we represent like resource 1, resource 2 and so on. So request stage is like, see, by directed graph we showing this way. So the process is requesting resource and assignment is means allocation. See, resource 1 is allocated to process, this we represent. See, process we represent in a circle and resource type we represent in a rectangle. So resource type with 4 instances. So there are 4 instances here. And P1 request resource. See, we showing this way. P1 is requesting resource. And if you want to show that P1 is holding a resource, then process is holding. See, arrow is like this way. Arrow is backward here. So P1, that means the process is holding the resource, particular resource. See here, this is the example of resource allocation graph which you already seen. So this is the process T2, process T3 and process T1. So this is like a circular wave. See, resource R2 holds process 2 and it is also wants resource 3. Okay, this is another example of resource allocation graph. So here we have resource 1, resource 3, resource 2 and resource 4. So in this resource allocation graph, process 1, see, there is one instance, that means resource 1 is only 1 and resource 3 is also only 1. But resource 2 are here 2 instances, 2 are there, like there are 2 printers or you can say, and resource R4 there are like 3 scanners. So process P1 is now allocated to resource R1 and resource R2. See, P1 is also holding R2. See, one instance it is holding. And P2 is allocated to resource 3. And P2 is also holding one instance of resource 2. And resource R3 is allocated to process P3. So this is how we represent. So this is another way, same example, but here process P3 is also holding R2. So this all, it goes into a circular way, that means it goes into a deadlock. So all the 4 conditions, if it is meeting, then mutual exclusion, hold and wait, preemption, no preemption and circular wait, then it enters into a deadlock. So if graph contains no cycle, then there is a no deadlock. If graph contains a cycle, then if only one instance per resource type, then it is a deadlock. Several instances per resource type, then possibility of deadlock. So if there are more number of resources, then every process will get the different resources, then no deadlock. But if there are no resources available, if the resource has to be shared, then there is a possibility of deadlock. So multiple resource, see, in this diagram it is a deadlock, and if there are multiple resources available, then it enters into no deadlock. See, resource R1 is allocated to process A and resource R1 is also allocated, means another resource is also allocated to process B, then it no deadlock. See another example on process resource allocation graph. See, R1 is assigned to process P2 and P2 is waiting for R1 here and R2 is assigned to P2. P3 is waiting for R1 and P3 is also waiting for R2. See. So in today's session we have studied what is a deadlock and how the deadlock occurs. If all the 4 conditions meet, then the system enters into the deadlock. And we have also seen how to represent the deadlock. To represent the deadlock, resource allocation graph is used. And in the next topic, we'll see how to handle the deadlocks. Thank you.